This is our video for Unit 7, Day 5. We're going to be looking at today is piecewise-defined functions. So first thing we're talking about what a piecewise-defined function is, what the definition is for a piecewise-defined function. This is a function that is defined by two or more different equations over a specific domain. So what this basically means is for different values of x, we're going to be evaluating the function differently using a different rule. So here's an example of what a piecewise function looks like. So we use this brace and we put all the different equations inside the brace. So all the different rules for functions on different domains will be in there. So this piecewise-defined function, we have fx equals x if x is less than 0, and x squared if x is greater than or equal to 0. So we have two different domains. We follow two different rules depending on where we're evaluating the function. So these individual domains where the rules change, these are called subdomains. These are the domains where a specific rule is taking place, called a subdomain. So if we're going to graph this function, we have to follow a different rule depending on where we are. So if the break here occurs at x equals 0, so if we think about vertical line x equals 0, to the left of this line, we're going to follow this rule here. If x is less than 0, then y equals x. So we just have the straight line y equals x. Right? We don't include 0 in the domain, so we put an open circle at 0. For the second part of the domain, it says x squared if x greater than or equal to 0. So starting at 0, going on out to the right, we graph the function y equals x squared, so parent quadratic function. So this is just an example of what a piecewise-defined function will look like. You can have two of these, you can have more than two of these. This is what a piecewise-defined function looks like depending on where you are, where your x value is. You're going to evaluate the function differently. So there's one example of a piecewise-defined function we've already looked at, and that's the absolute value function. This absolute value function is actually a piecewise-defined function. There's three different rules that the absolute value function follows. If x is a negative number, x is less than 0, the absolute value is the opposite of x, is negative x. If x is 0, absolute value is 0, and if x is positive, then you get back the number itself when you take the absolute value. So this is where the shape for our parent function comes from. For absolute value, we follow this rule. So x less than 0, we graph y equals negative x. Right at 0, we graph 0. And then to the right of 0, we just graph the line y equals x. So you can see that forms our parent function for the absolute value function. Right, so absolute value is a piecewise-defined function. It's one example of that we've already seen. So the two main things we'll do with a piecewise defined function is we'll look at how we evaluate them on different intervals and how we tell if they are continuous or not continuous. So one example, we have a piecewise defined function fx equals x squared plus 3 for x less than 0, and then 5x plus 3 if x is greater than or equal to 0. Right, so we're going to evaluate the function at two different points. We're going to evaluate it at -5, and we're going to evaluate the function at +6. So when we're evaluating, we have to look at which subdomain our input falls into. So here we're looking at -5, x is less than 0, so we have to follow this rule here, the first rule. So x is less than 0 falls into that subdomain. So then evaluating from there on out is the same as evaluating for regular function. We just take our input, plug it in for x, make sure we follow order of operations, and we get our answer. Right, we have to make sure we're looking at the correct subdomain and following the correct rule for where that number is. So for a +6, we're not going to use that top rule, we're going to use the bottom rule, because x is greater than or equal to 0. So depending on what number we're putting in, we'll actually evaluate the function differently, and that's one of the confusing pieces about a piecewise defined function is we're not always using the same rule. Depending on where our input occurs, we could be using a number of different rules. So besides evaluating piecewise defined functions, a lot of times we want to look at whether they're continuous or not. So what it means for a piecewise defined function to be continuous is two things have to happen. First one is each function has to be continuous on its subdomain. So each function in the piecewise rule must be continuous on its subdomain. So what that basically means is that we can't have any asymptotes or holes in the graph for the place where we're using that rule for the function. So anywhere we're using that rule in the subdomain, we can't have any breaks in the graph. It has to be continuous all along that whole subdomain. And the second thing is that the endpoints of each subdomain have to meet at the same point. So basically, each function needs to be continuous where we're using that rule, and the endpoints have to meet at the same point. So where we have the break in the function, we start using a different rule, they have to come together for it to be continuous. So we'll look at two examples, trying to find if these piecewise functions are continuous. So first one we're going to look at is the first example we had on the first slide. So x squared for x greater than for equal to 0, and x for x less than 0. Right, so first thing you think about is the domain for each of these sub-functions. Right, so the domain for the quadratic function is all real numbers. So it's obviously going to be continuous on this range here, and domain for linear functions also all real numbers. So it'll be continuous on its domain. So the first condition from that slide is met. They're both continuous on their subdomain. Right, there's no breaks in the graph that occur within either of these intervals. The second thing we're looking at is, do the endpoints of the function meet at a common point? So that means at 0, where the break in these rules occur, do they meet at the same point? So to test that, we basically evaluate both functions at 0 and see that they're the same thing. So we plug in 0 for x squared, and we plug in 0 for x, and in both cases we get 0. So both of these functions contain the point 0, 0. They meet at a common point, so this will be, like we saw on the graph, we'll have the line to the left and then the parabola to the right. They both meet at the point 0, 0, which is the endpoint. So they both meet at the common point. They're continuous on their subdomain. So this is a continuous piecewise function. So next one we're going to look at is going to have a little different rule. So we're going to have linear function x plus 2, x is less than 0, and then we're going to have the parent rational function 1 over x for x greater than or equal to 0. So again, we have to check both the conditions. So think about the domain for this function is a linear function, slope of 1, y-intercept of 2. Right, doesn't change. Domain will be all real numbers. For our parent rational function, 0 can't be in the denominator, so we have a vertical asymptote at 0. So it includes all real numbers except 0. 0 is included in the subdomain, so this is not continuous on its subdomain. So we already know this piecewise-defined function is not going to be continuous. Because this rational function is not continuous on the subdomain the interval is defined for. We can go ahead and graph it though and also take a look at the endpoint just to explain that piece of it. So we'll have the rational function for x greater than or equal to 0, so that means that the asymptote is 0. And then the positive branch of the rational function. And then x plus 2 for x less than or equal to 0, so we'd have y-intercept 2. I'd have an open hole there, and then a line with a slope of positive 1. This again, we see that don't meet at a common endpoint. This would be when we have this break in the function. The top rule, x plus 2, would contain the point 0, 2. Bottom function, the rational function, would be 0, and then infinity or undefined. It goes up along the asymptote, so they don't meet at a common endpoint. So this fails on both conditions. So either way, it would be not continuous. So we'll be working with this tomorrow in class, going through how we evaluate functions and also deciding whether two piecewise functions are continuous or not continuous. If you want to see some more examples of this, you can search for piecewise functions.